Our afternoon session. I hope that all of you enjoyed something quite different. I hope you succeed with your clubs and balls. I would like to introduce Michal Ludsky from Czech Technical University in Prague. He will give us his talk about laser ablation, fundamentals, principles. Michal,
Thanks.
please. Time is yours.
Yeah, thanks a lot. So, the topic of my presentation is laser ablation fundamentals and principles. And first of all, I would like to acknowledge my work to cooperation with Fachhochschule Vorarlberg, with Dana Seidinger and Johann Seidner, with whom we cooperate on ablation. We provide some simulation results and they provide the technology. Results presented within this presentation has been already published in a couple of conferences, among others at SPIE, Optics and Optoelectronics, and at Optickie Komunikace. What is ablation? It's actually a process of removing material from a solid. It can refer actually to any solid material going from very tough diamonds or metals to very soft optical glasses, as well as it can refer to materials with either high or low conductivity. What is ablation rate? It's a total mass which is removed by one laser pulse. And the main question is, what is it good for? One of the most popular applications is drilling a groove in a material, cutting material, cleaning the surface of a material, and probably one of the most spectacular one is printing three-dimensional shapes in the material. It sounds very promising. However, there are many issues that has to be solved about ablation process, and one of them is that actually when you look under the microscope, the surface ablated. The surface of the ablated material is actually not flat. There are some gain ripples on the structure. It's very confusing, especially in terms of what I already said, that it's used for cleaning the surface of a material. And we've noticed that it is actually not perfectly flat. There are either some strips on the surface or some pinholes which are located periodically on the surface of the ablated material. So, if we're talking in terms of microstructures, then you are able to ablate such a structure. But if you're going one step further and you want to have a look at the structure with the accuracy of nanometers or less, then the surface is not flat. And there are many issues coming into play on a vast scale, influencing the fact why do we obtain those pinholes and those strips that are responsible for some gain ripples, and it can affect the mode distribution. If you want to print, for example, a waveguide, design a specialty photonic crystal fiber or some specialty filter printed on the surface facets of a fiber, and so on. Then it will become an important issue. What is actually ablation? Low, because to find the reason of those gain ripples and those the roughness of the structure, we have to get a little bit more involved into the process itself. And actually, the drop of the deposited energy per unit of volume with the distance z to the surface is a function of the fluence which is absorbed by the material, and the fluence is defined as a radiative flux integrated over time. And there is another, so this is the fluence, and there is one more parameter which influences the ablation rate, known as the energy penetration depth. Is the energy over which the laser is absorbed. So there are two main features, and summarizing or trying to make a conclusion from this equation, we could conclude that there are two possible regimes of operation that can be considered. The first one is nanosecond laser pulse ablation, and the second one refers to femtosecond lasers ablation. Because, like I said, this is probably one of the key sentences here. The fluence is radiative flux integrated over time. So actually, it's great to have a huge flux, but if it's integrated over a very long time, then its ability to ablate the material is getting lower and lower. So, if we're going back to nanosecond lasers, which are those low price ones, they heat material, they evaporate material from going from the solid state through the liquid one to a gas state, or they can sublimate directly from the solid to gas. The disadvantage of this type of ablation is that you have to heat the material. So once the pulse goes deep in the material, the structure could eventually collapse. And if the structure collapses at very if the material conductivity is low, and it means that you won't overheat it that quick, and if the glass is soft, then this type of ablation is enough. Nanosecond pulses are enough for this purpose. But if we're considering, for example, metals, then the whole energy will very quickly be converted into the heats, and the structure which is printed will collapse in a very small depth. Here you can see the relations between energy transfer and time, and you see that, for example, heating the lattice by passing energy between photons and electrons is actually in the range of picoseconds. So if you don't want to overheat the material, if you want to ablate the material that fast that it won't, that there is not enough time to overheat it, then you should go to a pulse length much less than 10 picoseconds. And there are femtosecond lasers for this purpose, which are much better in terms of fluence, not because of the flux, but because of the flux integrated over much shorter period of time. Material is typically converted to plasma, and of course ablation is as well dependent on the penetration depth, as the same as in the case of the nanosecond laser ablation. This femtosecond ablation is known in literature as so-called cold ablation, because there is no transfer of energy to heat. You will not overheat this. So-called ablation allows to avoid plasma shielding effect. Coupling between electrons and photons allows transferring a part of the absorbed energy to the material lattice, and since the thermal phase change of the ablated material occurs after 1 picosecond, and depending on the material it can be 1 picosecond up to, let's say, 10 picoseconds, then the material won't be overheated, and the structure will not collapse. One of the key features is how can we improve the ablation process? How can we print the structures accurately, and how can we print the in greater depth? Because we're not talking only about printing some structure on the surface, but we want to print the 3D shapes. We want to create some waveguides, some filters, so we consider much greater depth. And the ablation depth is a parameter which depends on energy penetration depth and the threshold fluence. And one could conclude from this equation that there will be two possible regimes of operations. The first one, when the low fluence is applied, but the energy penetration depth is still efficient, which means that for specific materials, when the considered amount of energy can go much deeper than, for example, for some other material, you could focus on this parameter rather than on the threshold fluence. And another regime of operation, which is somehow more universal, is that fluence is significantly higher, either through increasing the laser flux or through reducing the time, the pulse duration, the time over which the flux is integrated. And in the same way, those lasers which usually have greater fluence, they usually have as well very good energy penetration depth. However, the process is even much more complicated. We have some threshold fluence beginning from which the process will start to occur, and this threshold fluence is different for different amount of laser pulses. In other words, using some, let's say, approximation, the effect is accumulating with the number of pulses incident on the surface. And one more thing, each pulse will have different impact on the ability of ablation. Yes, so each pulse will have its different incubation effect. So the first pulse will have much different volume that can be ablated by it than, for example, pulse number 100. So we have to consider not only the amount of pulses, but also the incubation effects, which are very problematic for simulations, because if you want to create a model of a laser, then you would have to consider that each pulse is totally different. You cannot just define the laser parameters and repeat the same pulse with some repetition rate, and that's enough. Then concluding and summarizing, the main phenomenon or the main tool to improve ablation efficiency is to reduce the pulse duration. Then you will increase the fluence because the flux is integrated over much shorter periods of time, and it works especially for metals or in general for materials with high conductivity, because in materials with high conductivity the thermal phase change occurs very quickly. So for metals it is recommended to use femtosecond lasers. However, for some materials, for some soft glasses with, for example, low material conductivity, it is enough to use nanosecond lasers. So, if we're dealing with the fluence, which was one of those two coefficients, then it's enough to reduce the pulse length. Yes, we're going to femtosecond pulses. But the other part, energy penetration depth, can we do anything about it? If we want to get very accurate ablation, we actually should do. And energy penetration depth, we've noticed that it is strictly, it is associated with the shape of the material that is ablated. It depends on what do you want to ablate. It's because imagine there is a laser pulse incident on the surface. It will sublimate some material, some volume will evaporate, and the following pulse have to propagate in the groove that, or in the area where the material is ablated. Maybe just one pulse won't be enough to ablate it. Maybe you would have to integrate more pulses and integrate the results. But once some part of the material is ablated, the next portion of pulses will propagate in different conditions. What I want to say is that you have to consider propagation issues. And once you, for example, drill a groove, which is, let's say, 10 micrometer depth, then you actually create a waveguide for laser pulses, and you have to consider the propagation effects that will strongly influence the possibility of drilling much deeper groove and ablating much greater and greater volume from the material. So, in our simulation node, we define the spot size as the size of the beam incident on the iron plate, and based on the pulse energy, we can achieve the peak fluence of the Gaussian beam, and energy of the pulse can be calculated based on the average power of the laser source and its repetition rate, which is 50 kilohertz. We use FDTD technique and material properties of the material. We considered actually iron plates and silicon carbide, which is used for some waveguides. We use material properties taken from the real measurement, as far as we're talking about the refractive index, and we use the polynomial approximation applied to the data. So we consider that that structure where we drill such grooves in the surface of the iron plate. We actually want to create a periodic structure because we want to deal later with some photonic structures. The average output power was 5 watts with the repetition rates of 50 kilohertz, and we consider the femtosecond ablation, which is called ablation for metals, and we are very interested in the energy penetration depth, which is associated with the propagation problems. And we modeled just the first pulse. We modeled one pulse. We ignore the incubation effects at this stage. And the laser pulse will propagate in the V groove. And we realized that actually the width of the groove and the depth of the groove will influence the energy penetration depth. So the first conclusion is that this sigma energy penetration depth is not a constant, which is it's assumed as constant in some publications, and it is assumed that the only tool that you have to improve the ablation process is the fluence through the pulse duration. And as far as we talk about the V groove width, we observe near linear evolution. So if the pulse, if the drilled groove is getting wider and wider, then actually you can drill deeper, and propagation issues could be neglected. But if you consider the dependency of the V groove depth, fixing the V groove width, then data fits the exponential decay, which means that if you are ablating structures that are pretty long or pretty deep, then going deeper, your ablation efficiency is reduced by propagation issues that create some limits. And we observe some interface with the reflected light. Yes, because this is how the volume of ablated material looks like. It reminds the V groove, and light incident on the sidewalls of the V groove will be reflected, and it could interfere with the following pulses which are incident on the surface. Yes, and the result is that there will be some local maxima of light intensity on the surface. Yes, we use a homogeneous laser with the spot size. The intensity of light at the spot size is homogeneous, but on the surface we observe local maxima of radiation that would burn more light in those pinholes here, and in fact you will produce some roughness of the structure because the light intensity is not uniform, is not homogeneous here. So this explains the roughness of the structure here, where you create either some pinholes or some strips on the surface of the ablated material. And last but not least, polarization of light is or could become a critical issue. We consider a cross-section of a photonic crystal fiber with the hole spacing of a couple of microns and core diameter of about 10 to 15 micrometers, and we deposit a gold layer which is non-transparent to light on the surface, and we want to ablate such periodic ripples. This is what is actually created as a side effect of the ablation process when you scan the surface of the material and you get some strips on the surface, yes? And we want to use it for good. And we notice that different light polarization will produce different strips printed on the surface, and as a result this could work as some filter. However, it will be strongly polarization sensitive or dependent. the strip width was 0.3 micrometer, and their spacing is half of the micro. So those values are pretty small for even for ablation, and this is one of the applications considered. And as a conclusion, it is worth to mention that in order to improve the ablation process, you could optimize the fluence of the laser by reducing the pulse length, which means that you integrate flux over much shorter time, and practically the best option is to use femtosecond pulses, which are suitable for most of the materials. However, nanosecond pulses are suitable for soft glasses, like for example fluoride materials, and those for mid-infrared. However, this is not the only tool that you have at your disposal. Another feature that comes into play is optimizing the energy penetration depth, and we've noticed that energy penetration depth strongly depends on the propagation issues. So you should monitor the shape of your material after you ablate some volume from it, because you will create something like a waveguide, which means that you will change the pattern of the laser, and we as well observe some interference of the light, which is backscattered from the side walls of the V groove, which is ablated by laser pulses, and as a result there were some local maxima of light intensity which do not correspond totally to the mode distribution of the laser output actually. And as a result you will print some strips or pinholes at the surface which are not desired. You could consider some applications like filters, but this is basically the matter of the future work. However, if you want to achieve very accurate ablation for nanostructures, you should optimize not only the fluence and the pulse length of the laser and the power of the laser or its central wavelength, but also you should consider the propagation effects, including laser polarization, which influences the energy penetration depth, which is, of course, is the property of the material. However, it could be a minor tool to tune your ablation exactly to what you want to achieve. And this is my conclusion about the topic. And thank you for your attention, and I hope you've got some questions to it.
Thank you for the presentation, and I'm opening the discussion. Please go ahead with your questions.
What is the minimum spot size you can do?
What is the minimum spot size we can do? Actually, we make simulations. We don't have technology. We plan to visit FHV in the summer, and experiments will show actually what is the achievable spot size. However, in terms of simulations, you're not very limited by the spot size.
Well, but if you would like to make, let's say, the smallest, or you are diffraction limited, right, with your spot size. So that's what I was curious if basically is there a limit for you?
What I want to say, when I go to a much smaller spot size, the simulation will no longer correspond to experiment.
Okay.
And I don't know where is the limit, but actually I can model even very small spot size.
Mm-hmm.
However, since it's not verified by experiment, I'm not able to say where is the physical limit of the spot size.
And what kind of field intensity you get in the focus?
What kind of?
Field intensities, E-field intensity you get in the focus.
These are the parameters which are modeled. Average power was 5 watts. 50 kilohertz is the repetition rate, and we consider 300 femtosecond pulses.
And what is the beam waste on this? Do you know?
Beam waste is associated with the spot size. Beam waste can be obtained from the spot size.
Yes. So if I want to calculate the peak power on the spot, I would need to know the size of the beam. I don't see the response. You have 5 watts average, right?
The spot size.
Yeah, power is arranged.
I don't remember what
Okay,
was the spot size. Actually, this is just one sample
What
simulation from many simulations performed.
So what is the
So I've
wavelength?
got like 100 pictures like this, and I just picked up
Yes.
one random from it, and I don't remember what
Yeah.
spot size corresponded actually to this one.
But the diffraction limit is lambda over d, so we can guess what is the wavelength of the laser.
The wavelength is
Oh, that's it. Okay.
and the pitch is even less than 1 micron. We go to sub-micron
Do you have
structures.
to focus so tight if you do these kind of tricks, or you just use more loose?
We use Gaussian pulses.
Okay.
I don't know what you mean by focusing.
Well, I'm assuming you use the lens, right, to make the intensity
Yeah.
higher.
We use femtosecond lasers, yes.
But the beam is big, so that's enough. If you have a cross section of the laser, I don't know. What is it? Violet laser?
Okay, but I model the spot size as I wish, and I don't have to. We don't think about how would I achieve it. I assume that they are able to achieve it because that's what they wanted me to model. The parameters were from FHV. If they claim that they are able to achieve this spot size, then we didn't involve in this question.
Yes,
It
sure.
was our assumption, actually.
Yes, okay, I can understand.
But of course, you have to focus it somehow.
I was just curious how, if you want to make very small holes like this, where that must be quite small.
It's actually in simulations you can do almost everything. We
Yeah.
don't have technology. We make simulations, and we hope to make such conclusions like you can do after
what they
we
want to
deal
do
with some
this, do you know?
technology.
What is the goal?
The goal is to design some filters which could be printed on for example, some photonic crystal fibers. They could modify input spectra, for example, or some slot waveguides. The first step was to answer what is the source of those of the roughness of the surface, because they scan the surface and they get some roughness, they get those pinholes, those strips, and they don't know why. And
I see.
and we actually answered these questions, and actually maxima of light intensity was obtained exactly at the places where you have those pinholes. So this was the first step, and it must be optimized if we want to think about the application.
Yeah, sure. Thank you very much.
Any other question? If not, thank you.